Mass spectroscopy. Okay. You recognize the little vehicle on Mars there, right? They have a mass spectrometer on there for sure. They're hoping to find what? What type of compounds? Carbon, organic compounds, right? And they think they found some, but you know, it's not so sure it has to do with life or anything. But how do they know what's there? It's a mass spectrometer they have on there, right? There's a lot of things you can do with a mass spectrometer. The advantage it has, instead of that FID, which was just a what counter? The FID was a carbon atom counter, right? It just burned stuff and counted the number of carbons. Well, this guy, he doesn't burn it. Instead, he blows them up. But he gets a fingerprint of every single compound. And he compares them to some big library, whatever is the best match for that explosion pattern. That's what he says he is in his library search. So it's a really powerful instrument. That's probably why it's so expensive, too. But drug abuse, monitoring, I'm sure, right? I mean, what else? It's the only type of detector you could have. What else could sense all the different possible compounds known to man? But this sort of thing. So I'm sure that he's in the New York subways and everything, right? People got to keep all that stuff maintained, so someone's getting paid some good money to walk around in the subways. But, okay. Here's the guts of it. Oh, my movie. We have a movie. I forgot about the movie. I don't know. We'll see. I don't think so. It's from NASA, so it's probably only in a minute.
What happens if you have something like this, and you want to find out if something like this is inside? Obviously, you can't tell just by looking at it, but if you separate things out, the answer becomes clear. Scientists have the same problem. How do you know if there was once water on Mars? Or, for that matter, life? Obviously, you can't tell just by looking at pictures of Mars, but scientists think the answer may lie hidden in tiny molecules in Martian soil. So, how do you take apart a molecule to see what's inside? Luckily, scientists have a tool to do just that. It's called a mass spectrometer, and it lets us take an extremely close look at whatever we're studying. And even though Mars immediately comes to mind, mass spectrometers are used in multiple NASA missions. They're also used in labs for hundreds of scientific purposes. But the important question is, how does it work? Today we'll be looking at a special kind of spectrometer called the Quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars, but also answers to bigger questions about the universe. And all by studying something as tiny as a molecule.
Okay. So, he mentioned a mass spectrum. Okay. But, Nyla, what is it? Wake up then. What is a mass spectrum? I'll give you, what are the axes? This one is signal, but what's the x-axis? Probably. It's a mass spectrum. Mass. Yeah. Okay. Oh, she's seen this before. Yeah, they have M all over Z. Is really what they are. But Z is what? Now, he kind of gave a hint in the movie. These fragments have a charge, so Z is just the charge. And then it's always +1. So it's never... So the Z is always +1. But little m is going to be the mass. Okay? And it's really not, really don't think of grams or anything like that. No, it's just think of bigger pieces and smaller pieces. That's really all it is. Yeah, it's really grams, but it's not calibrated to say this is so many grams. That's not what it's after. Okay? It's after getting all the little pieces and, well, getting the explosion pattern of a molecule is what it's kind of after. So what would an explosion pattern look like? Well, some of those, some of these fragments, a bunch of these. All it is just a bunch of straight lines. Okay? So the signal, so you're going to have a lot, I don't know, like maybe, look at this mass right here, whatever that number is. The signal's pretty high, so there's a good number of them, right? That's all really it is. Okay? It's a fingerprint for that molecule. If you ever have that molecule, he will always give that same fingerprint for a mass spectrum. Obtaining a mass spectrum starts with ionization, though. There's numerous types of ionization. Okay, which does ours use? Electron impact. Where is it? Oh, right at the very top. Ours uses electron impact. So it's going to, whatever comes off, the GC has to do its work first, though, right? Because this guy is not a chromatography machine. He doesn't separate mixtures. No, he just analyzes and blasts things up and gets fingerprints for molecules. So you have to have pure molecules entering this thing. So in front of it has to be a chromatograph, liquid chromatograph, gas chromatograph. That has to do its job and get all these pure molecules to be shooting out of that. Mixtures, the chromatography has to be done before you shoot it into the mass spec. And then the mass spec blasts it with electrons, right? Okay, and that's how it's going to ionize and make these patterns. Okay, you blast something with so much energy, it just falls apart. And that's the magic of it, is that it falls apart the same way all the time. Molecules do. With regard to electron impact as an ionization source, the book gives this equation. What do you think these terms represent? Like, Kimberly, what do you think this big M is? Or well, E negative is probably the electron, right? That's coming from this ionization source. It's going to blast into the, what's coming off the column? The whole bunch of, and they're all identical, molecules, right? So big M is the molecule. And it gets blasted by one of these electrons. And then it loses an electron, right? It becomes a cation. But what's the dot mean? A radical. Okay. John, is a radical something pretty nice and stable that's going to hang around for a while? No, it's extremely unstable. Very energetic, right? Okay, so that's the first step. During electron impact ionization, it appears, Miranda, that it's most common to make, bless you, which one? Yeah, cations. Okay. Electron impact ionization occurs once in it's a million, right? Therefore, it is, or is not. What would you say? Not. It's not. But the dang thing is so sensitive, you really don't care. Okay, I mean, 1 in a million is fine. Okay, some disadvantages. We're going to see what this means, but you don't want to lose this. That's a bad thing to lose, because a lot of times you're like, I don't know, the dude's on Mars, right? Trying to figure out what stuff is. And you don't want to lose something called the molecular ion peak. All it is pretty much this guy. His mass is really what? What would his mass be? The total, which we call the add up all these molecular weight, right? That's the molecular weight. If you have an unknown compound, it'd be really nice to know what its molecular weight is. So if he doesn't fall apart, if the detector can detect m dot plus, He just lost an electron. You can't tell. Electron is so light. What's more massive, by the way, a proton or an electron? Proton. How many, by what factor? Like 1,000 or so. So protons are a lot more massive than electrons. But anyway, so this guy, his mass would be the molecular weight, the molar mass. So you really, if the detector, if he totally, completely, 100% falls apart, that's called losing the molecular ion peak. We'll talk about that. It's coming up. So it doesn't really help if you lose it. Molecular weight must be less than 1,000 grams per mole. Another disadvantage. All right? It's probably getting into this whole, we've seen that number before. Where did we see that number before? It caused problems with you can't make a gas, right, without having it decompose. That was that molecular weight limit for a GC in the inlet, kind of. Okay. Yeah, so I think 2 and 3 are kind of the same thing. You got to make it a vapor, and a lot of times it's just going to degrade before it gets ionized. If it degrades before it gets ionized, you're finding the mass spectrum of all degradation components, not the molecules. Okay. Some terminology here. Daughter ions. Anna, you have any guess what daughter ions probably are? Right? This molecule comes off the column, 1 in a million gets blasted by this high energy electron, right? And the thing falls apart into ions, which are just called daughter ions. So
the parts of the molecule?
Yeah, the fragments. Yep, the fragments are the daughter ions. Okay. So here's some more terminology. In that mass spectrum, Jeff, we've got a base peak. And he's referred to right here. Why do you think they picked that one, the 91, as a base peak? It's the smallest. Yeah, it's the largest. Yeah. Right? So the peak that's the largest is just called the base peak. Okay. Peak 106 is referred to as the molecular ion peak. So that's the compound's what? Molecular weight. So you could add it all up and you get 106 for its molar mass. But take a closer look at the rest of this question. Right? Oh, sorry. I'm not here yet. So there's our molecular ion peak. And not all mass spectra have one. Sometimes the thing completely falls apart. Why do you think these guys who are looking for an unknown, why would it be really helpful to find the molecular ion peak again? Because then they'd know the unknown's what? Molecular weight. So that's kind of why playing with terminology. Oh, the molecular ion peak, don't lose them, we need them. But it's not really your choice. Either you detect it or you don't. How is it possible to have a peak? Here it is. How is it possible to have a peak with a greater mass than the molecular ion peak? Look at that guy right there. How could you have a daughter ion more massive than the compound itself? Adriana, how could that even be? Experimental error. Give you a hint. It starts with an I. Isotopes, right? Are all carbon atoms created equal? Are all hydrogen atoms created equal? Are all chlorine, right? Oxygen, are they all? Some are more what than others? Heavier, right? And why? They have more what? Neutrons, right? In the nucleus of that molecule, right? Like carbon 13, right? 1 out of every, 10,000 or so atoms. Okay. So that's why It's just 1 over, because carbon-13. So you can't, that's why all these, look at the base peak. He even has it too. Isotopes. Give that daughter ion another one, an extra one at 92 because of isotopes. So you're okay? Some components of a mass spectral detector. Okay, here's all the answers up on top. I'm going to give you some time, a couple minutes here, and you see if you can figure out where all this stuff goes. Okay, like the vacuum pump and the gas chromatograph, computer readout. See if you can fill them in, and then I'll ask you. See if we can figure them out. An answer for everything? Or should we just ask Casey? Huh? Yeah. Yeah. Yeah, that was a computer readout. Okay. Should we see if we can figure this out? Yeah. Okay, let's ask Natalie. Let's just go 1 through 8. What did you put for number 1? Yeah. Vacuum pump. Well, if you say 1 is vacuum pump, then what would be this funky blue line coming from the vacuum pump? Okay. But why? Right? Yeah, that little blue line is going to be the molecules and the ions passing through. But vacuum pump sucks everything up. So it can't be originating from there. This big box has to be the what? Gas chromatograph. That's where the whole thing starts. Where's the gas chromatograph? Here he is. He's number 1. Okay. So the GC's doing his job. You have pure molecules shooting out of that thing into this mass spectral detector. So, Kat, what would you say 2 is? Molecules, good. 2 is molecules. How about Kathleen, number, where are we at? 3. It looks like 4 is before 3. We should probably change those numbers, but that's okay. What'd you say 3 is? What'd you say? Ions. Yeah, because, right? This guy is what? What 3 ions? Because 4 is the, Miriam, 4 is the, you have molecules on one side, ions on the other. Yeah, the guy, the ionizer. Exactly. 4. Okay. So now we've got ions. We're at position 3, Nyla. So okay, so now we're going to, now these ions are going to inside this 5. What's 5? Yeah, quadrupole ion analyzer. I guess the hint is like quad, 4, right? 4 rods. Okay. Jamesa, these ions are passing through the quadrupole. Now we're at 6. Yeah. Only the mass, only the ion it's looking for, that mass makes it through. The rest, nope. 6. And then we have 7, Pablo. The successful ions, then they go to 7. What's that? Yeah, the detector. Okay. Then there's a little dashed line going from the detector to number 8, Urandi. 8 is probably, yeah, computer readout. So that only leaves 1 left, everybody. That means 9 has to be the vacuum pump. Okay. So there's a quadrupole mass spectral analyzer. Okay. If you go upstairs and everything's plugged in and running, you hear this constant noise in the background. Right? This vacuum pump is just constantly running. 10 to the minus 5 to 10 to the minus 8. You should say millimeters of mercury or torr. But it's really extremely low pressure. Amanda, what's atmospheric in millimeters of mercury? The stuff we live in. How many millimeters of mercury pressure is that? Anybody remember? It's the 760 millimeters of mercury is what, and we're above sea level, so we're probably around 740 or so, right? A little lower pressure. That's to suck out a lot. So what harm would a little air do? It absolutely does not want any air in there at all. Casey, have any guess what air would do to this? Mess with the ion path? Yeah, there would be no ion path. It can't go. I mean, look at all the stuff between Miranda and I. It's thick air. There's no way a single molecule can travel from myself to Miranda. No way. It's going to hit air, right? You have to have that thing empty completely. The technical jargon is mean free path. The distance between collisions. It has to be huge. It has to literally be the size of the table. You can't have molecule has to go from here to here without any collisions at all. Okay. How does a quadrupole mass analyzer work? Okay, so now I need some help. Let's get How I like to tease Big Bad John. So Big Bad John, you go out in the hallway. Then I need 4 people. Wait, like you 4 right here. You guys come on up. Maybe not. 4 might be too many. Yeah, you go in the hallway. Take this. Oh no, come over here first. Otherwise, it's not gonna make sense. Okay, so you guys, you have to hold this quadrupole. I need 1 person to hold it down here, right? Come on. You only have 1 hand? This isn't gonna work. Okay, you gotta hold the other one though. All right, that end. Then someone else, another person over here. Now you have to make that nice quadrupole thing. Okay. And then probably you got this side. You gotta make that quadrupole thing. Maybe we need more people to do this. All right, is this making sense? Here, yep. Okay. So you can see the quadrupole. Okay, now I need Nyla.
You hit
and then,
Oh, God.
You hit me, I swear.
I don't know, Amanda, over here. Right?
John's throwing.
Pablo. Okay, now everyone's got their own function here. Now you see what the different parts are here. Okay, just stay in the back so far. John's going to be the mixture, right? He's a molecule. You can't see the ions. You can't see the daughter ions, right? It's just all in there, right? So, but he has to be injected onto the GC, and he has to get separated from everything else. So, you're out here, okay? Nyla is going to be the what? The ionizer, right? Now, she's only going to literally hit them 1 out of every how many times? Million, right? But that's all we really need, okay? Now, these guys are going to be applying energy. Okay, once we get these parts going, I'm going to need some more help here. Kathleen. Okay. So when, Adriana, come up here too. I'm going to need, we pretty much need the whole class to get this to work. Okay, keep coming up. Okay, so when she does blast it, you guys got to get the fragments. How many different fragments do you have in there? Like 1, 2, 3, 4, like 5? Right? Well, you guys just have to pull double duty. So come on this side. So you're kind of out of the way yet. You're not used until she actually blasts them. So then you're going to pass through here, and I'm going to show you how to apply your you actually have to bounce it through, and I'll show you how. Okay? Amanda's the detector. So anything does make it through, she's going to detect it. Nice big signal on the computer. This guy is my big what? Vacuum pump. Okay? So what does not get through that detector, he's got to suck up. Right? And it ends up just following this little tube on the back of the GC. It goes up to a fume hood. I don't know if you ever noticed that. There's a little line that goes all the way up. Okay. So let's go ahead and get started. So first, you're injecting. Yeah, turn the phone. Turn the vacuum. All right. So he's injected, right? The GC, the column, is doing its job, right? Okay. Now pure molecules are coming through. Okay. Whiff.
What?
Whiff.
What does that mean? Hit him.
You whiff. 1 out of a million. You miss.
You go like this.
You miss.
Yeah.
Miss, right? Miss. So where does this stuff go?
Into the quadrant.
Into there?
Okay, it can try fitting in here. Now, to go from here, this is applying, this guy, it's pretty much, imagine bouncing. You need so much energy to bounce it through here. And that's what these guys are all supposed to be applying, right? And it's trying to go from 1 mass to the other. This is way too massive. Pablo just ends up sucking it out, right? It doesn't make it through. Maybe, I don't know how far it gets, but it definitely doesn't get to the detector. Okay? So, but all these types of molecules are coming off the column, so keep going. All right? All right? Because this impact thing never stops, right? Those electrons are constantly flying through. All right? So, okay, just nail them. Okay, now you fragment. Okay, now you guys get your fragments. Okay.
Oh, that's heavy.
Okay, let's not do the ping pong ball ones yet. Let's do, yeah, something like that. Okay. We'll each grab one fragment, otherwise it gets confusing. Okay. So all these fragments are flying through here. Okay, now you just try to bounce them. Try to bounce them through. Yeah, you're going to need a hell of a lot of energy, right? Hold it up high so people can see it.
Careful, Kim.
Right? No, yeah, you don't want to break the tabletop. But the point is, these guys are applying only so much energy to get it to bounce. If they're applying the energy for a wood to bounce, right, that'll make it all the way through. So just kind of bounce it on through there. Well, no, just kind of your hand or something, right? But it's up here, right? Well, kind of hold him down so she can make noise with it, right? But he's kind of bouncing in here. Wood energy. And then, you ready? Detector. But the steel ball energy, there's not near enough energy, right? For it to even make one bounce through there. Pablo does his job. He sucks it up, right? But all these fragments are going through at the same time, right? Now this guy, he's changing his bouncing energy. I think it takes a hundredth of a millisecond. It's really fast how fast this thing scans through all these different masses. So so grab some other fragments. All these fragments are coming through here at once. Most of them Pablo's sucking up. But let's pick you guys are doing super ball energy, right? Or ping pong ball energy, whatever, right? So we just pick one to bounce through there. It's only ping pong ball energy. Whoa. The idea is it's ping pong ball energy. Super ball, he bounces really easy, right? So one little bounce, you're applying way too much energy. The quadrupole is, right? So he's going to suck it up right away. Okay? And keep going. Now he doesn't have near enough, right? He doesn't even get a single bounce. Okay? But now ping pong ball energy. Okay? But you have to get them all. Look at all these fragments of the ping pong ball. There's a bunch of them. So you're right on ping pong ball energy. So now it's perfect. It's perfectly matched, right? Ping pong ball energy is perfectly matched.
These two?
They all have to go through, right, at the same time, right?
That one got stuck. It's broken.
But the ping pong ball one, much higher signal because look at them all, right? So that's it. Thank you very much. Oh, thank you, sir.
You get extra credit points.
Well, you should. Okay. Now, when we did our carbon dioxide on the gas chromatograph mass spectral analysis, we got a peak. And he looked something like this. He did not look like a mass spectrum. Right? Didn't he look like this? Do you remember that? But we're using the. How can it look? How can it not look like this? What's going on there? What you were looking at is something called the total ion chromatogram. If you take a mass spectrum, right? Because that's what this guy is detecting, a mass spectrum. You take all these heights and just add them up. At that instant in time, that's going to be your signal. So what this guy really is a whole bunch of mass spectra, right? Maybe I can make it look better, right? You're not seeing anything, right? So what you should be seeing is a bunch of dots, but the computer connects them because it wants you to see peaks, right? So, but each dot is the sum. Like if you take one of these, it goes to there, right? Because each one of these is a mass spectrum. So there's a lot of data in here. Every single dot is a complete spectrum. They're huge, huge files. Okay, but if this is one pure component, then all these mass spectra should be identical, right? Because it's all the same thing. If the GC did its job, if it didn't, well, these mass spectra are going to be changing. Okay, and that's one way to tell if, if you have co-eluding peaks and things. Okay, so that's the difference between a mass spectrum and a TIC, a total ion chromatogram. Okay, so when we did our carbon dioxide analysis, we were looking at total ion chromatogram, total ion chromatograms. Okay. So let's say, I don't know, let's pick on Pedro. Pedro he's not selling it, he doesn't want to get in trouble, but he has this little drink. It's a Christmas time, makes a little drink for everybody, and everyone on campus is really happy after they drink this little drink, right? So what is he doing something illegal? So we put it on the little machine, right? Put it on the machine, especially the mass spectrometer, and see if there's anything fishy in that thing. So we get a whole bunch of peaks, and we'll do a library search on every single peak, right? See what the mass spectrum library search thinks it is. Okay. And let's say we come up with something, ooh, right? It's, I don't know. Yeah, something bad, right? Would it hold over in court? Would it go over in court? We'd say, hey, man, $60,000 instrument. Everything's all nice and calibrated. Right? Everything works great. Would he get in trouble? Or do you have to do something more? The question, what we're trying to answer is this one.
It just tells you what it is.
Yeah, well, what it is the problem, right? Just by doing this library search, is that all we need to do? What the library search is it's just like this great big software program, all these files. And all the computer did is it looked at this mass spectrum of Pedro's fishy compound that we're worried about, right? And it just says that, hey, he matches really well with this file. Well, how'd you get that file? That file was made by somebody's GCMS across the world over here, and they sell this big library search. So it's not, that's all it means, is that it matches. It's very likely. It matches great, and it gives you percentages and all the statistics and things. But you don't know for sure. It's just a software thing. He matches his. So what you have to do is you have to go out and get the stuff that you think he's messing with, inject it yourself, see if the retention time has to be the same if it's the same compound. Not only does the retention time have to be the same, whatever that time is, but the mass spectrum has to be the same too. So you shoot that pure compound on your GCMS, compare retention times, and compare mass spectra. That is the only way to show that, yep, Pedro, you shouldn't be doing that. All right? Yes?
So, when this is applied in the real life, do people just have like a warehouse of like pure drugs that they
Well, no. Well, they could if they're doing that every day.
Yeah,
For us, or research, whatever you're doing in the summer, you do the library search and it tells you what it thinks it is. And that's the one compound you have to buy. That's it. You just go out and buy that one compound. And then you put it on here, inject it, compare retention times and mass spectra.
I feel like this is great for drugs and narcotics.
All right.
Probably
Now, where we run into trouble is the DEA. I can't compare some things. Like when we were doing some sewage analyses and other sorts of things, and some other projects. It kind of nips things in the bud because they can't buy the pure compound. But if you're not going to publish, you can still present, but it's not as strong. Okay, so that's about it. Have a good day. See you tomorrow morning.